Writing chemical reactions is like writing a recipe in order to cook a meal. We have to know the type and quantities of ingredients that are actually needed to produce a certain quantity and type of meal. The most critical skill that you need for chemistry is the ability to write and balance equations. It is impossible to study chemistry without having this ability. The law of conservation of matter is articulated as matter can neither be created or destroyed by ordinary chemical means. A chemist must account for all matter that's originally present, starting out as reactants or reagents, and be able to track where that matter goes in the formation of products. This happens without a gain or loss of matter. Now, there are many definitions for what a chemical reaction is, but fundamentally, it's a process where atoms that are actually present in the reactants, they're rearranged to produce a new arrangement in the products. In order to keep track of all the matter in a reaction, chemists must produce a balanced equation while using coefficients that specify the number of molecules of each chemical entity. The coefficient is the number in front of the compounds and molecules that actually tells us how much of each substance is present in the reaction. For example, in a saltwater aquarium, the waste products of fish and invertebrates are actually broken down by bacteria into an extremely toxic substance called ammonia. Most of the ammonia reacts with water to form ammonium ions, rendering it less toxic. From there, other strands of bacteria convert the ammonium into less toxic nitrogen-based substances such as nitrite and nitrate ions. Now, if we examine the balanced chemical equation of the first step of this process, we see that ammonia plus water yields ammonium ion plus hydroxide ion. Even though there aren't numbers written before each compound, there is an implied coefficient of 1 in front of each molecule. So when you would read this reaction, you should read it to yourself like 1 molecule of ammonia reacts with 1 molecule of water and produces 1 molecule of ammonium ion and 1 molecule of hydroxide ion. Another way that this reaction could be read is 1 mole of ammonia reacts with 1 mole of water to yield 1 mole of ammonium ion and 1 mole of hydroxide ion. In chemical reactions, you're going to use arrows, and they're not just for decoration. They communicate some very specific things about what is going on chemically. Arrows in a reaction represent what reactants yield, or what they produce, or what they form. Now, a singular arrow implies that the reaction may go to completion, meaning that all the reactants get used up and you have 100% products. Some reactions between chemical substances instantly go to completion after they're mixed. Others go to completion after a significant amount of time has passed. And some reactions go to only a partial extent regardless of the amount of time that actually passes. Now, in a situation like this, you're going to see 2 anti-parallel arrows that are written. The reality is the only way to truly determine the outcome of a chemical reaction is to do it in the real world, to actually perform it in a laboratory setting. But the beauty of being able to write balanced equations is that we can make predictions as to what that outcome would be without having to really conduct the experiment ourselves. Now, here is critical information for you to understand. Since all reactions have to obey the law of conservation of matter, the number of atoms on each side of a chemical reaction must be balanced for each and every element. The number of atoms of any element occurring in a given substance is found by multiplying the subscript of that element by the coefficient of the molecular formula. Let's review how this works by analyzing the chemical reaction for cellular respiration. Here we have 1 molecule of glucose plus 6 molecules of oxygen yield 6 molecules of carbon dioxide and 6 molecules of water. Reading from left to right, let's get in the habit of lining up our elements. Here we have carbon, we have hydrogens, and we have oxygens. On the left side of the arrow, we see that we have a subscript of 6, so we would write down 6. On the right, we have a coefficient of 6, which applies. It's distributed to both the carbon and the oxygen in that molecule of CO2. So we would say that we have 6 carbon. So the carbons are balanced. Now let's go down to hydrogens. In glucose, we have 12 hydrogens, and on the right side, we have 2 hydrogens, but there's a coefficient of 6. So 2 times 6 is 12. So the hydrogens are balanced. Next, we go to the oxygens. On the left, we have 6. in the glucose molecule, plus notice we have 2 oxygens times a coefficient of 6. So 12 plus 6 is 18. On the right side, we have 2 oxygens and carbon dioxide, but there's a coefficient. So 2 times 6 is 12, plus the oxygen in water times the coefficient, which is 6. So we have 12 plus 6 on this side, which equals 18. So as you can see, all the oxygens are balanced. The whole reaction is balanced. When it comes to the actual art and science of balancing chemical reactions, there are several methods that you could use successfully. Now, for the most part, I've always used the following strategy that I'm going to share with you. Take it for what it's worth. I think you'll find that it works quite well, but of course it does require practice. Very first thing, when you're looking at a chemical reaction, you need to write out all your elements in a list and separate the reactant side from the product side. You need to do this initially while you're learning this process. Eventually you do it so much you could pretty much do it in your head. But right now, we're going to do it step by step. First thing, we're going to balance all the elements in this order. First, we'll balance all metals. Once those are taken care of, we're going to move to balancing all the nonmetals with the exception of hydrogens and oxygens. We're going to save hydrogens for third. We'll balance all the hydrogens. And for oxygens, we'll balance them last. It's important to note that you'll not always be able to start at the top of this order and work your way down just in one shot. The reality is that often you will numerically adjust an element and end up affecting an element that you previously balanced. I recommend going to the very top of the order and starting over, just working your way back down. Let's get some practice together. Here we have a molecule of ammonium dichromate, and it's breaking down into nitrogen gas, water, and chromium 3 oxide. So let's line everything up. By looking at the reactant side, let's start with the metals. Well, chromium is obviously a metal, so we'll write that one down. Then we have nitrogen. That's a nonmetal. Any other nonmetals? Well, we have hydrogens and oxygens. We hold on to them. Nitrogen is the only nonmetal, so now let's move to hydrogen and then oxygen. We have 2 chromium on the left. How many on the right? It has a subscript of 2, so chromium is balanced. Nitrogen. Remember the subscript distributes to that nitrogen. So we have 2 on the left, and we just happen to have 2 on the right as well. Then with the hydrogens, we can see that 2 times 4 is 8. On the right side, notice that in the water molecule, we only have 2. So we need a coefficient, a multiple, that will yield 8 hydrogens. And that multiple is the number 4. So 4 times 2 is 8 on the right, and then 2 times 4 is 8 on the left. Hydrogen is balanced. Next we have oxygens. Notice we have 7 oxygens on the left, and then how many on the right? Well, we have in the chromium 3 oxide, we have 3. And then if you look at the water molecule, it shows as 1, but you have to remember the coefficient is distributed. So technically we have 4 oxygen there. So 4 plus 3 is 7. So on both sides of the chemical equation, you have 7 oxygens. This chemical reaction is officially balanced. Example number 2. Here we have phosphorus plus oxygen yields diphosphorus pentoxide. Jump in right with the nonmetal phosphorus. And then the only other element, we don't have any hydrogens, but we do have an oxygen. So on the right side of the equation, we have 2 phosphorus. So let's go ahead and put a coefficient of 2 on the left side. Then as we move on to oxygen, we see on the right side of the equation we have 5. Going back to the left, there isn't a whole number that we could use to multiply by this 2 in order to get 5. We need to be thinking, okay, well, what's a common multiple? And the answer is 10. So what if we went to diphosphorus pentoxide and we put a coefficient of 2? Well, now we've actually affected the phosphorus that we already balanced. So let's go back to the very top. Now on the right side, we have 4 phosphorus, so we got to add a coefficient of 4 to the left. So now phosphorus is balanced. Go back to the oxygen. On the right side of the arrow, we have 10 oxygen. Let's look at the O2 molecule on the left. All we have to do is put a coefficient of 5, and now we have 10 oxygens on the left side. So this chemical reaction is balanced. So the key takeaway is to understand the law of conservation of matter. The number of atoms on the reactant side have to equal the number of atoms on the product side. Number 2 is the strategy for balancing. My strategy that I've showed you, I've been using it for years and it's always served me quite well. Again, the first step would be to make a list of all of your elements, and then from there start balancing. Metals first, then move on to nonmetals, then hydrogens, and then oxygens. So keep practicing and you're going to find that you develop this ability very quickly.